Welcome to the Maitrix EC-TPU demo. The EC-TPU is our error correcting TPU, which is essentially a high performance matrix multiplier unit. This demonstration will show you how our basic technology works and how we can actually perform error correction of matrix arithmetic. We start off first by running our demonstration program. So I will go to Visual Studio Code, hit run, and as you can see, this is our demonstration screen. Our demonstration is actually based on a Stratix 10 FPGA, and we're running on Ubuntu right now, and essentially we're on a Stratix 10 GX development card, and we wrote some basic C program that actually accesses this development card and is able to interact with our matrix multiplier. And in this particular case, we have a demonstration that we created that was going to show our error correcting arithmetic. First, I'll go ahead and show you our setup real quick. So I will slide the screen here real quick. And as you can see with the camera here, we basically have our open PC with our Stratix 10 GX development card in there. You can see our water cooler, and also you can see that we have an expansion card connected to the development board where we're going to actually introduce overclocking as part of this demonstration. So a little bit closer view here, give you some idea of our system. Okay, moving on very quickly. Basically, what you are seeing here is an 8x8 matrix, and we're doing an 8x8 matrix multiply in this particular demonstration. Keep in mind that our matrix multiplier can also do much larger matrices using tiling, for example. So an 8x8 matrix computation can be performed multiple times across larger matrices, and so essentially matrices of any size can be computed using this hardware. What's unique about our matrix multiplier hardware, if you haven't already seen some previous demonstrations of our technology, is that the matrix arithmetic is not binary arithmetic, but is called RNS arithmetic. And RNS stands for residue number system. So we chose the residue number system because in this particular case we get a carry-free number system, and the architecture is such that because there's no carry for multiply and addition, essentially we can break up our matrix multiplier into a series of matrix multipliers, each matrix multiplier handling one digit of our word. So as you may know, any computer has a word size, and in our particular case we have a word size of 10 digits. What this allows us is that the base word size is 8 digits, and that gets us a 32.32-bit fixed point precision. And by adding 2 additional digits, this gives us the redundancy required to perform error correction. So real quick here, if you look over to the right on our numerical error statistics, we're showing some of our capabilities here, and we're showing that even when you start out with a single precision floating point number for the matrix values, once you do a matrix multiply and you convert that to the residue number system, and you do a complete matrix multiply in the residue number system, and then we convert that residue number back into floating point, it is still more accurate than floating point alone. And this kind of gives us an example. These stats running under this red box here demonstrate our accuracy is even higher than the original number system that we started with. And this is possible because the matrix multiply doesn't round on any of the calculations until the final dot product is complete. And I can increase the range real quick of these numbers, so if I hit special key, then you'll see down here that the numeric range is changing, and by doing so I can basically let's see, basically increase the range of the numbers that are being computed here. Another thing I can do real quick with this demonstration on this key menu real quick, I can actually hit the F key and I can speed up the demonstration. So essentially there's less delay between the display periods that are being shown. And then of course I can hit the S key and also slow these computations down. So if I slow them down, then it's a little bit easier to see the computations that are going on. Every once in a while in the green here, which is the resulting matrix, every once in a while you might see a red number come up. We flag the red number in two cases. In one case, it's the one calculation that was not as accurate in residue as it would have been in floating point. Or if it's red and it's a very large number, that usually indicates that there was an error that was detected basically in this in the matrix multiply. And that's exactly what this demonstration is about. So moving over real quickly, I'll just speed up this a little bit so we can see this. And the first demonstration, really quick, I'm going to go ahead and insert an error. And so one of the first errors I'm going to insert is just a random dot product error. And I can do that by hitting the P key. And as you can see now that there's yellow tiles appearing in this larger green matrix multiplier. And what that is indicating is that it's indicating that an error was detected, but that it was corrected. So whenever you see a yellow tile, we detected an error, but we corrected it in real time. One of the nice things about the error correcting technology at Maitrix, it's forward error correction, and these are pipelines that are sitting on the output of the matrix. So as the dot products are exiting the matrix multiplier, they go through the error correction unit, and if an error is detected in the result, it can be detected or can be corrected. And generally the condition for correcting an error is that we can correct a single digit. Now every once in a while you'll see that a red tile comes up. A red tile indicates that more than one digit was in error. So for example, 2 digits are in error. In that particular case we can detect that an error occurred, but we cannot correct it. But detection of errors is also a very valuable property, so that when you're doing matrix multiplication, we can both detect errors and in many cases correct them. So right now the errors that are being injected by a circuit that we put into the matrix multiplier demonstration that actually injects errors into the dot matrix results. And so this allows us to get a simulation of actual errors that are occurring in the matrix multiply, and we'll show how our system actually is correcting them. In the middle of the screen here, where you see these very, very small tiles, we're actually showing which digit is actually in error. So now if I slow this down, I can actually go into a single step mode here, and every time I press the space bar I just get one run, and it's a little bit easy for me to explain exactly what's going on. So in this particular case, as I single step, I've got one error. So on the left, on the status grid, on row 6, column 1, you can see we have a yellow tile, which means an error was detected and also corrected. And here in the middle of the screen, we see that that error actually occurred on the digit 7. So we know what position of the matrix the error occurred, and we know what digit that error occurred. So as I single step through more, you can see that the random error injector is injecting errors in random locations. So in this particular case, we see errors, 3 different errors were detected, all 3 were corrected, and of course one was at row 0 column 1, the other was row 2 column 1, and the last one was row 1 column 4. Notice what digits are actually responsible for those errors. Now another thing I can do real quick is I can actually increase the error rate, and so by doing this, let me go ahead and get out of single step mode, and I will just hit R again, and now it's running automatically, and I can go ahead and increase by this arrow key the probability. So I'm increasing the probability that errors are occurring, and you can see that there are more errors occurring. Let's see. I can also try this. Okay. I guess it was the bracket that I was supposed to press. So by pressing the bracket in this demonstration, we're getting more errors. Now, as you notice, if I go back to single step mode, you'll see sometimes I get a red tile. So in this particular case, on row 1, column 4 of the status grid, a red tile is being indicated. And if you go ahead and look at all the different digit matrix multipliers here in the middle, you'll see that that one position, there's a red indicator in every one of those exact same positions, what happens to be row 1, column 4. And the reason is that when there's more than one digit in error, we can detect that the digit was in error, but we don't know, we can detect that the dot product was in error, but we don't know what digit contributed to that error. In this particular case, we actually draw a red tile in every one of the digit matrix multipliers. So it gives you an indication. Since we don't know, we go ahead and label each one red. So once again, as we single step through here, you can see different patterns based on the error generator that's inserting errors into our dot matrix results. Another type of error, we'll go ahead and turn off the dot product error, and we can now move over to a readout error. And a readout error is a little bit different because in this particular case, readout errors occur when the buffer that is actually feeding the data into the matrix multiplier ends up reading out incorrectly. And in that particular case, you'll get a whole row of errors. So for example, in this case, we see row 0 of the status grid is all yellow. And we can also note that it's actually digit 4. So the readout buffer for digit 4 read out incorrectly. And as a result, since if you know how your dot products work in a matrix multiply, you're doing a row times a column. So in this particular case, the row was wrong, and the row readout was wrong for every dot product across that row. And since it's a single digit, in this case digit 4, that was an error, even the readout error can be completely corrected. So while every one of these dot products was wrong, they were corrected by the error correcting pipeline. So if I continue to single step through here, we'll see different errors. And as you can see, some of the row errors are coming up in different locations. Now I can increase the rate that these errors occur, and so in this particular case, you'll see in this particular case a red row. And so for the red row, what we have here is that more than one readout for more than one digit was an error, and so as a result we have an entire row in the matrix status grid all red. In this particular case, we detected that all those dot products were an error, but we were not able to correct them. So if I hit E, we can also do the same thing for columns. So as the same similar situation, we can also inject column readout errors, and in this particular case you can see the entire column 2 is yellow. In this case, once again, all the dot products in that column were in error, but they were all corrected. So again, in a similar way, you could pass through these and discover that the random error injector randomly puts in errors, and we can increase the probability. And as you can see, once we increase the probability of column readout errors, then we of course get many more that are red, which were the uncorrectable columns. Okay, and of course these types of error injections are quite high in terms of the probability. The last thing, one of the things we can do is we can turn on all of the error contributions. So here I can turn on the dot error as well as cycle through all errors here, and you can see as I walk through we're getting different types of errors, and just depending on where those errors are landing on the digits, they can be either correctable or uncorrectable. So as you can see, there can be quite a few errors in the matrix multiplier, and we could still get the exact result back if they were correctable. Now, real quick, I will go ahead and turn off our demonstration of injected errors. Keep in mind that the errors that I showed you were injected by circuits that we placed in there. Now, to show you something a little bit different, we will now inject errors based on the frequency. And so we're going to overclock this circuit, and I'm going to show you that real quick, that we have a function generator here. And this function generator here is going to allow me to increase the frequency of the FPGA core clock. That's the clock that's running the matrix multiplier. And we're going to overclock this and inject real errors based on overclocking. So going back to this, we will get out of the single step mode, and I will begin to overclock this thing. So as I'm turning up the frequency, right now I am overclocking, but the FPGA is doing very well, and modular computation, which is all, residue number systems all based on modular arithmetic, so there's no carry from digit to digit, but modular arithmetic itself, it happens to be quite reliable just on its own. But here I'm starting to overclock, and at some point we will introduce actual errors based on clocking. Okay. So here what you see is errors that are random errors just introduced by overclocking. At this point, I'm actually 37% over the rated clock speed of the FPGA compiler. So in this particular case, we are running in excess of 400 megahertz. So our matrix, every matrix multiply is performed in 9 clocks. Every 8x8 matrix multiply takes 9 clocks, and that is being performed at over 400 megahertz. So that's roughly 2.5 nanoseconds times 9, and so that ends up being, quite quick. That's about 9 plus or 18 plus 5, so you're looking at about 23, 24 nanoseconds to accomplish one matrix multiply, 8x8 matrix multiply, at a 32.32-bit fixed point precision. As I increase the frequency a little bit more, then what you can expect is you'll expect that there's going to be a breakdown, obviously. So more errors are occurring, of course, and then you're starting to get red tiles because you're getting more than one digit in the same dot product position in error, in which case you're got an uncorrectable error. So now I've really jacked up the frequency quite a bit more, and I'm at a point here where these are real errors, not our error simulators, but these are real errors due to overclocking of the matrix multiply. So at this point I'm 40% higher, and that's about, let me calculate that for you. So that's 1.4, and we had a baseline running at 300 megahertz, so this is 420 megahertz here. Once again, as I decrease the frequency now, and I'm decreasing the frequency as we talk, you can see that now we're getting less errors due to overclocking. So that pretty much concludes our short presentation of Maitrix's error correcting TPU. Thank you very much.